Okay, we have a series and we want to find out if it converges or diverges. So we want to check if we can do the integral test. Can we do the integral test? Well, first of all, is this monotonically decreasing? Is it always decreasing? It seems like yeah, because if we plug in a bunch of numbers, the denominator is definitely going to grow faster than the numerator, so each term in the sequence is going to get smaller. So that's our first check. Our second check, are all terms going to be not negative? So yeah, they're all going to be not negative because we start at 1, we go to infinity, we've got no negatives in there, nothing that could make it negative. So we're good. We could do the integral test to check for convergence or divergence. We do the integral test by taking the integral of that. We tend to, out of convention, change these for x's just because it's not wrong, but we're just more used to using x's. We go from 1 to infinity. We can't work directly with infinity there, so we replace that with t. We let the limit as t approaches infinity stay there, and now we can actually do this. So how do we do this? I think, well, we need to notice that we could do arctangent with this one. I know it's like not that easy to see if you're not used to arctangent and stuff, but the integral of this is very similar to the integral of 1 over x squared plus 1, which we would know is arctangent of x. So we just need to get it into a form that exploits that. So let's look at what we have here. We have x, and then we've got x squared squared, right? That's the same as that. So this is the same thing that we have there. We're using x, so this is dx. So let's make a u sub, and let's try to get that x over there to go away in some way. So I would probably let u be x squared. U equals x squared, du therefore equals 2x dx. And so that's going to allow us to make this substitution and have an x go away, because when we take the derivative, you know, we have to be strategic here. We take the derivative of that, and that becomes just 2x. And that's what we wanted, to just get this x to go away. So at this point, you have to think strategically on this level. So we can solve for dx. That's du over 2x equals dx. We make that substitution, and we make the other substitution, which was to have u in there. We're still taking the limit as t approaches infinity. X's here go away. We can bring out the 1/2. So we have 1/2 integral from 1 to t of 1 over u squared plus 1 du. Now we have exactly what I was talking about that I showed you earlier, that form. This is just arctangent of u. Once we evaluate that integral, we get arctangent of u. We get 1/2 multiplied to that. We can make our substitution back because we didn't change our bounds. We just have to now change back to x squared. And this entire thing is going to have an upper bound and a lower bound. We subtract the lower bound from the upper bound. Limit as t approaches infinity. So what happens? We have 1/2 arctan of t squared minus 1/2 arctan of 1 squared. We plug in infinity because we're taking the limit as t approaches infinity of that. And what's going to happen? We plug infinity into there, that's infinity squared, which is just infinity. Arctangent of infinity is something we need to know. So we have our graph. If we don't remember, we have to think visually. We have to think, what is arctangent? And we know that arctangent is tangent sideways. So it's a little like that. Maybe this is like steeper, but you get the idea. This is what it looks like, and we have like a horizontal asymptote right there at pi over 2. So if you go to infinity in that direction, you are going to reach a limit, which is pi over 2. Pi over 2 is what happens when we plug in infinity. And we're multiplying that by 1/2. So that's going to give us pi over 4. That's what this is. So this is pi over 4. And we're subtracting from that other term, arctangent of 1 squared. So arctangent of 1 would be just some value here. We can't know it unless we're like specialists in arctangent or have a calculator. So that's just, you're going to take that at face value. But whatever the case, this is your answer. This is your answer. So it didn't diverge, which is the thing that we wanted to check for, which is most important. So it converges. Our integral converges, and so therefore our series also converges to whatever that